Hey everyone. So up to this point, everything that we've been dealing with has had vectors in either in the x or the y direction. Here's an xy plane. So we've dealt with vectors that are either going this way or going this way. But in real life, these vectors are typically going to be at some angle, and so we need to determine a way that we can figure out how to deal with this, and it's something called vector components. And so we can break it into x and y directions, and then we can deal with it a lot easier. So let's go back and let's think about displacement. Remember, displacement is a vector. So we're looking at the change in position, but it's a vector. And so if I go from some start to some endpoint, there's basically an infinite way to do it. But if I define my coordinate system to be typical xy, like that, then I kind of want to go sideways and up down. And so there's really two ways that I can do this. Let me get some lines on here. So I could go right, and I could displace this way, and then I could go up, and I would end up at the end. And then let's get some arrows on here to show that it's a vector. So I could go right, and then I could go up, however many units that is. But I could also go, I could do the opposite order. I could have gone up first and then gone right. Something like that. Draw some little arrows on here. The end result, though, is the same. So the end result is this displacement vector, which would be the diagonal of this thing. So it would be that. Let's draw an arrow on there. Okay, oops. So we draw a little arrow. And so what I see is that my total displacement, remember the displacement doesn't matter which way you go, it's beginning and end. So my displacement vector here is going to be in this direction right here. This is my vector right here. And so this vector is at some angle theta. And in fact, you know what? I'm going to cross this out. We're going to call it displacement. I'm just going to use r. It doesn't matter. R's, I'll show you why, because I'm going to use x and y down here. But my total displacement is this vector right here. And there's, again, there's two ways to do it. I'm going to look at this bottom one, though, because if you notice what this does is it makes a right triangle. And so that makes it easy. And so what we had is we had some displacement in the x direction. I'm going to call it r, displacement in the x direction. And then I had displacement in the y direction, r, y. And now I have a right triangle with three sides. These things are called components. My x and y direction. So when I have something at an angle, I can break it down into an x direction and a y direction. Conversely, if I know the x and y direction, I can put it back using Pythagorean theorem into the resultant, we call that. So this is called the resultant. Resultant vector. Let me say vector. Looked like velocity. And notice it's the same over here. So this is ry as well, and this is rx up here. So I can use any combination of these. I could have done x this way and y this way and done my result here. However, I typically will be drawing right triangles like this. So I usually don't do y and x like that, but you can. It doesn't matter. All the math works out. We'll get into the trig and how to figure out this stuff here in a bit. Okay, so that's for displacement, but this actually applies to any vector. So if we think about force and we're pulling a box by a rope and we're applying some force called F at an angle theta, then we can break this into components. So we would probably say that my x and y are going to be this way. So what we have to do is we have to figure out what's our force in the x direction. And so what I'm going to do is I'm just going to draw a right triangle here. So I know that this force is pulling it in this direction along the x direction. So that would be my force in the x. So then we put a little x to indicate. And then it's also pulling it up. I know I'm not drawing very well, but you get the idea. So this would be the force in the y direction. And then there's my right triangle. So now I can use some trig and figure stuff out. What if I have multiple? So here we have three different forces all acting on this object. If we wanted to figure out, the acceleration, or if it's balanced, or whatever we want, the first thing we have to do is break it into some components. And so looking at F1, again, I'm going to set my coordinate system to be typical. So F1, I would get some force in this direction. This would be F1 in the X direction. And then I would get F1 in the Y direction here. And then my angle would be right here, theta. Call that theta 1, because we'll have different ones. And we typically, when we talk about angles, we'll measure it off the horizontal. So I'm measuring off this way. Like for this one, this is force 3. So notice force 3 is pulling it in the X direction the opposite way. So this is F3 in the X direction. And then it's pulling down. So F3 in the Y direction. And the green one is F3. And so my theta 3 would be right here. That would be theta 3. So notice it's measured off the horizontal, not all the way around. I mean, you could, but we typically will just measure there. And then all of our triangle stuff will work out. Keep in mind, like this one, because of the way I defined it, so this would be a negative value, and this is going down, so this is also negative. With a net, we could call it like a negative angle, but don't worry too much about getting all this stuff. Two ways to draw this, so I could go down and then I could go over, but I typically am going to do my X first. So this would be F2 in the X direction, and then down. So there's F2 in the Y. And there we go. Now I can start working with components. My angle here would be up here. That would be theta 2. Okay, so this is going to be a pretty common step, is breaking out all the components, and then what we'll do is start putting them together in Newton's first or second law. But how do we figure out the actual value? Okay, so how do we determine these actual vector components? So let's do a quick review of some trig, and then we'll apply it. So we're looking at a right triangle given sides A, B, and C, and an angle theta. Remember that this one is the hypotenuse of the triangle. So we have a couple things. Number one, we know that these three are related by the Pythagorean theorem. So we know that a squared plus b squared is equal to c squared. And so I could use that if I wanted to know, if you give me these two, I could tell you what this side would be. That implies that c is going to be the square root of the sum of the squares. So I say the square root of the sum of the squares. I'll say this a lot. So if I want the magnitude of the hypotenuse, it's always the square root of the sum of the squares. The square root of the sum of the two squares. It's an easy way to remember it. So the magnitude of this thing will always be the square root of the sum of the squares. And that comes from Pythagorean. And we could solve, we could move things around, but these are the two that we'll be using mostly, because this one will tell me the magnitude of a force. Okay, then we have trig. So trigonometry deals with ratios. And if we look at the ratio of two of the sides in relation to an angle, the ratio is always the same. So if I were, for instance, if I were to double this triangle so that it comes way out here and comes down, then the ratio, let me just do that. Let me make it a little bigger. So now I have a new triangle, but now I have like a B, let's call it B prime, and I'll call it C prime. C prime is all the way out here. What it says is that the ratio of B to C is going to be the same as B prime to C prime. So the ratios stay the same. That's what these trig functions do. And so we have relationships, and it relates these three sides in relation to this angle. So it depends on where this angle is on what we call things. Typically, we'll call across from the angle, we would call that the opposite side, because it's opposite the angle. And then right next to it, but not the hypotenuse, we call the adjacent. And then the other one is the hypotenuse, the long side, opposite the 90 degree. So these are my three sides. And then we have relations between them, which are given by 3 trig ratios. So the first one, we could look at the opposite and the hypotenuse, and that's called the sine. So we would say the sine of theta, the angle, is always going to be B over C, so opposite over adjacent. I'm just going to abbreviate over hypotenuse. The opposite over hypotenuse, which in our case is B over C. And that would be sine theta. And then, yeah, I'll get into, we can solve these things. Okay, so then I can go to the adjacent and the hypotenuse. So we link these two. Now we'll link these two. So since this is next to it, that's called co. So that's cosine. Cosine theta is going to be the adjacent over the hypotenuse. So in our case, it's A over C. And then the last one that we'll deal with is going to be these two, tying these two together. So it's always opposite over adjacent, and that's called tangent. We just use tan as the abbreviation. So that's opposite over adjacent, which would be B over A. All right, I want to show you any of these it works, but this is how we can solve these things. Let's just do, say, cosine. Cosine theta equals adjacent A over C in this case. So if I wanted to know the value of this and you gave me this one, then I would just multiply this to the other side. So I get C times cosine theta is equal to A. Then I could solve for C. I could say, well, okay, but C is going to be A over cosine theta. So either one of these would tell me one of the sides given the other and an angle. But you can do this with any of these. The other thing that we need to know is how to figure out the angle. But I think we'll just do that when we need it. We'll introduce that. So now we can apply it. So here's a force. And so what I want to do is determine an expression for the components. So the first thing that I would do is draw in the actual components. So I see that this force is applying a force this way. We'll call that the force in the x direction. And then I get a force in the y direction. Force in the y. And what I want to do is I want to determine each of these, given this one. So given the hypotenuse, how can I figure out the force in the y direction? How can I figure out the force in the x direction? So I'm going to throw on some things. This is the hypotenuse. My angle's here, so this is the opposite. This one is next to it, so it's the adjacent. And then I want to relate these, not this way. We don't do x and y. I don't know either of these. I know this one. So for f in the x direction, since it's adjacent and hypotenuse, that's my cosine function. So I get the cosine of theta is going to be the adjacent, which is f in the x direction, my x component, divided by the force. Rearranging this, so moving this over here, I get force times cosine theta equals the force in the x direction. And this is the magnitude of the force, whatever it is. And that would be my fx. Now we can go to fy. So fy is opposite in hypotenuse, so that's sine theta. And that's equal to the opposite over the hypotenuse, the force. And I can do the same thing here. Sine theta is equal to the force in the y direction. So we end up with these two things. In general, this is going to hold. This will be true. So the force in the x direction is going to be, the force, and when I say force, I'm talking about the magnitude of this, times cosine theta. And the force in the y direction is going to be the force times sine theta. Now there will be instances where these flip, I always just draw the triangle and deal with it. But in general, we'll be able to do this. Okay, so let's apply this. So here I have a box hanging by a rope to some ring or knot or something, and then that knot is then attached to two other ropes, and the whole thing is suspended from a ceiling and a wall. And then I'm given these quantities. So I have a 500 Newton force here at an angle of 37 degrees. And then I have a 412 pulling this way at 14 degrees. Those are off the horizontal. And what I want to know is what's the tension pulling down. Okay, so the first thing to do is we need to define our coordinate system. So we'll call it, just keep it standard, y and x. So what I really need is I'm going to have to break this up into components. I need this tension 2 in the x direction, and then I need tension 2 in the y direction. Likewise over here, note that your tension is this way. So I'll get tension 3 in the x direction and tension 3 in the y direction. And then my tension 1, notice, is all in the y direction. So T1 is T1 in the y. And so really what we want to do is, if you just look in the y direction, this one right here, since it's down, has to balance out this one plus this one. So really all we care about is the y direction. The x direction, this one should be equal to that one. We can check it. But what we do is we deal with these things separately. So let me just draw this. And what we're going to do is we're going to do, let's do the y direction. So everything in the y direction. And so our law here, since it's in equilibrium, would be that the net force in the y direction is equal to 0. There's no acceleration, Newton's first law. And so what we have is we're going to now write our forces. So tension 2 in the y direction, and that's positive because it's up, plus tension 3 in the y direction, minus tension 1 is equal to 0. Why is that negative? Well, because it's down, so that's a negative. Okay, I want to find tension 1, so let's just move it over. And notice there's no y here because this whole tension is all in the y direction. So if I move that over, I get tension 1 is going to be equal to tension 2 in the y direction plus tension 3 in the y direction. All right, so now we need to break out the components. And since my angle's over here, since my my triangles are drawn according in the typical fashion with x down here and y over here and my angle over here, then I can use these equations that we just did. I don't really rely on those too much, I just do them again. But tension 1, so tension 2 in the y direction. Tension 2 in the y direction, so that's opposite and hypotenuse. So it's this times sine theta because it's opposite. So it's T2 sine 37. I'm just going to put theta 2 plus the tension in the y of 3. So it would be opposite. So again, it's sine. So it's T3 sine theta 3. Now we can plug in all our numbers. So tension 1 would be the 500 times sine 37. That's in degrees. Make sure your calculator's in degrees when you do these. And then tension 3 is 412 sine 14 degrees. And I'm going to stop there because now it's a calculator problem. So just keep in mind, make sure that your calculators are in degrees. It says degree on your calculator up at the top. It's like up here. It says DEG, not RAD. Physics C, they'll be moving. Sometimes you'll get these calculators that are going to be in radians. So we'll deal with that later, next semester. Anyway, those are vector components. So we break everything into x and y, and then we'll deal with it separately. I guess I should have, you want to see the x direction? Let me erase this. So if we wanted to do everything in the x direction, I'll do it up here, x direction. Then we also know it's not moving in the x, so the net force in the x direction is also equal to 0. So looking at just these two right here, this one and this one. So I get T2 in the x direction, that's positive because it's right, minus T3 in the x direction is equal to 0. And then I can move it over. So T2x equals T3x. And then using the trig, these are next to the angle, so that's cosine. So it's T2 cosine theta. 2 is T3 cosine theta 3. And then I could solve for whatever I wanted. Anyway, this is how we do it. We do y direction and x direction, do them separately. And sometimes you'll use Newton's first law in one of them, but Newton's second law in the other. Anyway, there you go.